For Algebra 2, we're going to look at our topic 5, which is studying radicals and also functions and their inverses. And we're going to do a review of many of the important ideas that we haven't done in a while. So let's go ahead and take a look at this. So first of all, we're going to review exponent rules, which goes way back to first semester and then also pulls in a couple new things for this semester. So if you multiply two things with the same base together, the rule is that you're going to add the exponents. Whereas if you divide the two of them, the rule is that you're going to subtract the exponents. Now, if you have a negative exponent, in this case it's like it's in the numerator because it's like over 1, you then flip it to the denominator and make it a positive exponent. If it were in the denominator, start with a negative exponent, you'd move it to the numerator and make it a positive exponent. And then this was the new one. This is, just so you know, this is really, the way it should be written is m over n as the exponent. It kind of looks like it's not the exponent, so let's make sure it's distinctly the exponent. When you see a fraction in the exponent, the denominator represents the index of a radical. So this is going to be, the denominator is your index, and then the numerator is going to be the exponent on the outside. So that's the new one to introduce with radicals, is that that denominator becomes the index of the problem. Now this next one, what we do for this, and I'm going to add into this, I'm going to add a coefficient of 2 here. So if you put in these, having a t on the outside of the parentheses, you bring it into each one of the factors, both in the numerator and denominator. People forget to bring that t into the constant sometime, so that's why I want to add it. So this is going to be 2 to the t power. Now I'll bring the t into the x. It's going to be x to the t power. Now I'm going to bring it into the, the c. So it's a c to the t power for the next one. Now the x, when you bring it in and there's already an exponent there, you multiply exponents. So it'll be t times the m, multiplication when you bring it in. And same with the y. The y already has an exponent of n, so I'm going to have the t times the n as part of that. All over, down at the bottom here, it's like d to the first, so d, bring the t into it as an exponent, and then z already has a q on it, so I'm going to multiply the t times the q as part of that. So the main idea there is when you bring in an exponent to each of the factors, if it already has an exponent, multiply by it. If it doesn't have an exponent, it's implied to be a 1, so take it and put it on that base. Anything to the 0 power, you strip away all the factors and you're left with 1 as an answer. So anything to the 0 power except for 0 itself is equal to 1. Now let's review a little bit about functions. This is we've done functions before, but we did a big review because we wanted to introduce what's called the inverse function. And so for a function, it's for every input and usually that input is an x, there is one output, which is usually a y. Now we could use other variables, but there's an input and an output. Every x is paired with just one y. That means we have to remember the x values are not repeated. If you see any ordered pairs with two different y's but the same x, that is not a function. Now when we have an inverse function is where you take the x and the y in whatever form it is and you have them swap places. So the x and the y swap or change places. Okay, so let's do some examples with some functions themselves. So here's a function, just as a reminder what this notation means. Let's say we're doing f of 3. F of 3 would be you take 10 times 3 and subtract 15. That's 30 minus 15 is equal to 15. So you put the value in for it. Now to help with this g of x, just as I use this, I'm going to actually convert this into fractions, just it might help us with some of these problems. So another way of writing g of x, it's the same function. You just, instead of 0.25, let's write that as a 1/4. And instead of 0.5, let's write that as a 1/2. That just might help you understand. You can do it with either way, but when you have decimals in inverses, it can get confusing. So I'm going to use fractions. It might lead to a clearer example. So I want to do the inverse of g of x. I'm going to use this form. So I'm going to first of all write it as y equals 1/4 x plus 1/2. Now remember, to do the inverse, the x and y swap places. So I'm going to put the x here equal to 1/4 times y plus 1/2. Now I want to get the y by itself. It's in the middle of this expression. So I'm going to go ahead and subtract 1/2 from both sides, equals 1/4 y. And now to get rid of the 1/4, I could either divide both sides by a 4th, or what would be better is if I multiply by 4. It's the same thing, multiplying by the reciprocal. So I'm going to multiply both sides by the 4, and I'm going to get 4x, 4 times -1/2 is -2, equals y. So that's my inverse function for it. And I can rewrite it. This is the notation we use, a little -1 listed up there to indicate that it's an inverse, and then we write the rule out, 4x minus 2. Now, here's another thing we did. We've done it several chapters, but this idea of a composition of functions. This is not multiplication. The open dot refers to composition. Now, what that means for us is that we're going to take this, and I like a different notation first. That open dot, I find, is not as easy to follow as writing it this way. This is another way to write composition of functions, and this implies that the g of x, this function is going into the f of x. So if I list the two functions, f of x equals 10x minus 15, and g of x, I'm going to go ahead and use this form just because you can use either one, is 0.25x plus 0.5. What we're going to do is we're going to take the thing on the inside, we're going to take this function and we're going to put it in for x in the other function. So what this will look like is I take the f of x and I list it. I don't put the x there, I put a parentheses because the x is being substituted out. This is going to be substituted in. So I get 0.25x plus 0.5. And now I do my multiplication. 10 times 0.25 is 2.5x. Okay, 10 times 0.5 is equal to 5. And then minus the 15 at the end here. And then simplify it for my final answer of 2.5x minus 10. That's what the composition of f and g gives to me. So that's review of functions. Let's go ahead and do one with just numbers rather than having just the x's involved. This one, what you're allowed to do is just say, hey, let's do the g of 14 first. Whatever's on the inside, calculate what that is. So I'm going to put the 14 in. So g of 14, I'm going to put that in here and get a 0.25. And instead of an x, I'm going to put in a 14. And then plus 0.5. Now you can do that on your calculator. You take a quarter of 14 and add 0.5. And when you do that, you should get just 4 out. So that gives us a nice clean 4. So if I'm doing f of g of 14, like the problem's asking me to, I'm going to go ahead and put in the 4 where g of 14 is, because that's what we calculated it to be. And now I'm going to do the same thing by substituting 4 into the f of x. So I'm going to take 10 times, and instead of an x, I'm going to put 4 in there, minus 15. That's 40 minus 15 is equal to 25 for an answer. Good, so that's a specific example about doing it with functions. Now, we're back to inverses here. So we talked about inverses here. It still applies when we have ordered pairs. For these, we swap the x and the y for here. Well, here, we're just going to swap each x and y in the function. Now, first of all, this is a function, because notice that the x values, no x value is repeated. But now we're going to swap them, make it 8 comma 4. This is the inverse. This one will swap. We have 14 comma 10. Next one is 12 comma negative 3. Then 14 comma 20. That's my inverse. Now notice that this inverse is not a function, because you notice these two 14s, it's repeated. So it is not a function when asked that question. Good. Now we're going to move on to some examples of simplifying and solving with radicals. So we did a lot of work here. These didn't have radicals, so we started out talking about up here our rules of exponents, and we used that to transition into radicals. So we're going to use all these. And we started talking about just functions and inputs and outputs as part of that, and then how to do an inverse. So that was without the radicals. Now we're going to actually simplify with radicals in it, and also with solving with radicals. Now, this one here, I'm going to do a side one off to the side here. Just a reminder, the goal is when you're simplifying is no square roots in the denominator. Okay, so we want to go for simplifying no square root in the denominator. Now, to do that in a simpler problem, if we had, say, for instance, 7 over the square root of, let's say, 11, if you had that kind of problem, all you need to do for that, to get rid of the square in the denominator, is we're going to multiply by the square root from the denominator, top and bottom. Now, this fraction, we can multiply by it, because that's equal to 1. And when you multiply by 1, you don't change the value, but the form of it's going to change. It's going to be equal to it, but it's going to be in a different form. So in the top, I'll have 7 square roots of 11 over the square root of 121. We're going to multiply those two together. And then the square root of 121 is equal to 11. So I get just 7 square roots of 11 over 11 when I do it this way. Now that's when you have a single term, just multiply by it top and bottom. But when you have 2 terms, you have to multiply by what's called the conjugate. So I'll put that word here, conjugate of the denominator. If this is 5 minus the square root of 3, I'll multiply by 5 plus the square root of 3. And I do it top and bottom because you have to have this equal to 1. Notice that that fraction equals 1. So if I multiply by 1, doesn't change the value, it's just going to change the form. Now let's go ahead and I'm going to get rid of that just because it's kind of in the way. But what I'm going to do now is multiply. I'm going to treat this like the distributive property. So negative 2 times 5 is negative 10. Negative 2 times the square root of 3 is negative 2 square roots of 3. Over, and in the bottom, I'm going to multiply this by double distributive. 5 times 5 is 25. 5 times the square root of 3 is 5 square roots of 3. Negative square root of 3 times 5 is negative 5 square roots of 3. And then negative square root of 3 times square root of 3 is negative square root of 9. All right, so that's going to be, notice in the top, I just leave it. I can't combine these two. So negative 10 minus 2 square roots of 3 over. Now our goal, remember, was to get rid of square roots in the bottom. This one we got rid of the square root at the bottom. Same value, different form, no square root at the bottom. Here, we got a lot of square roots there, but what happens is, by multiplying by the conjugate, these middle terms cancel out. So I've got a 25, and then you still have the square root of 9, but we know what the square root of 9 is. We can make that equal to a 3. So 25 minus 3, so that equals negative 10 minus 2 square roots of 3 all over 22. Now, that's simplified with no square root in the denominator, but it's not simplified for the whole fraction because there is a factor here of 2 in everything. So we should take out a 2, make it negative 5 minus the square root of 3 all over 2 times 11, and then the 2's cancel. And so your final answer is negative 5 minus the square root of 3 over 11. So that gives us our answer for it. So both of them, we were able to get rid of the square roots in the denominator. That's how you simplify when you start off with a square root in the denominator. All right, lastly here, let's solve an equation with a radical. It's important to remember we need to check our answers, because in the process of solving these, we could create extraneous solutions, solutions that are answers to what we create, but not answers to the original problem. So when we do this, to get rid of a square root, you're going to square both sides. So I'll just list it as the next step. Take this side and square it. Take this side and square it. That process could create those extraneous. Now go ahead and square it. Square a square root. You get just the radicand, the thing underneath, equals x squared. Now we should recognize when we've got an x squared and other terms that this is a problem that we could get 0 on one side and either factor or use the quadratic formula to solve. I'm going to focus on factoring. So I'm going to subtract 5x from both sides. And I'm going to subtract 36 from both sides, bring them both over onto the x squared side, and I'll have 0 over here. Now let's go ahead and factor that. So x squared will be x and x. Two numbers that multiply to give you negative 36, add to get negative 5. So you could go through the list of what multiplies to get negative 36, and you can stumble upon that's negative 9 and positive 4, that when you add them, you get negative 5. Now when two things multiply to equal 0, zero product property tells me x minus 9 has to equal 0, and x plus 4 equals 0. So both of them set equal to 0. Add 9, you get x equal to 9. Subtract 4, you get x equal to negative 4. Now you got to check them. So checking this one, you go ahead and put 9 back into the original. So x equals 9. You're going to get the square root of 5 times 9 is 45 plus 36. Does that equal 9? If you put in 9 for the two spots where there's an x, well, does the square root of 81 equal 9? It does. So this one checks out. Let's try the negative 4. You can probably suspect that maybe that might not. Sometimes both of them work though. Sometimes neither of them work. In this case, one's going to work and one's not. Because when I put in negative 4, I get the square root of 5 times negative 4 is negative 20 plus 36. Does that equal negative 4 when I put in negative 4 for x? Does the square root of 16 equal 4? And the answer is no. So this one doesn't work. So this one we get rid of. So our only answer is 9. So these are review problems from our radical and also function where we looked at, especially at inverses, some of the key types of problems that we do for this chapter.